So we can predict if a salt solution could be acidic by looking at the cation of the salt. In general, you'll find that cations that belong to group 1A or 2A, so that would be the most common ones you'll encounter. Sodium, that belongs to group 1A, potassium, group 1A, magnesium is group 2A. Those are in your periodic table, the columns in your periodic table. They will not hydrolyze, so you can't expect these ions to give you an acidic solution. So if you have a sodium salt or a potassium salt or a calcium salt or a magnesium salt, you can't expect that solution to be acidic. However, ammonium chloride is slightly acidic, iron chloride is slightly acidic, and this is iron 3 chloride. And the reason is as follows. Ammonium, NH4+, okay, can actually react with water molecules, and what happens is an H plus can hop over from an ammonium ion. Remember, ammonium has surrounded by 4 hydrogens. You can get that from an ammonia with an H plus attached to it, right? So that's ammonium ion. So one of these hydrogens, like let's say this one, can hop from the ammonium ion to a water molecule, giving you ammonia, leaving behind ammonia, NH3, and produces H3O plus, hydronium ion. Okay? And so when that happens, you have an acidic solution. That can lead to an acidic solution. Now, what about iron chloride? Most transition metals actually in water, they're actually bonded to several water molecules. So for example, iron is actually surrounded by 6 water molecules. It actually has a covalent bond with 6 water molecules. So iron, when we say iron with a +3 charge, okay, it's actually a shortcut for this more complete formula. This is called the hexa-aquo iron 3 ion. So this is hexa-aquo iron Roman numeral 3 ion. And what happens here is when these water molecules are attached to a positively charged ion like iron, okay, it becomes easier for a proton, an H plus. Okay, remember, H plus is just a proton without a hydrogen atom without its electron, right? So and we frequently use the word proton to refer to H plus. So the H plus from one of these water molecules that are attached to the ion can easily hop over to another water molecule. So let's say there's a water molecule from the solvent. One of these H pluses can hop onto that. So that leaves behind, that will give you Fe, and then that's H2O. 5 water molecules remain intact. One of those water molecules is now just going to be an OH. And the whole thing will now have a charge of +2 because an H plus has left. And that H plus attaches itself to this water molecule here, and that gives you a hydronium ion. So this is the reaction that you write, chemical equation you write to represent the hydrolysis of iron +3, iron 3 ion. Okay. Oftentimes, this is abbreviated so that we don't have to worry about how many water molecules are really here. Okay, then you can just write it as Fe with a +3. In effect, what it has done is it's pulled a hydroxide away from a water molecule, so to speak. You might say that ends up with FeOH 2+, and then that liberates an H+. So this thing right here is an abbreviation for the reaction we just wrote earlier. Okay, so basically a cation, you can say, okay, can pull away a hydroxide ion, you might say, from a water molecule, freeing up an H+, causing the solution to be slightly acidic. Now, what about negative ions? If you're negative ion, like we said that negative ions have a tendency to can possibly make your solution basic. And the reason for that is you have something negative, okay, it can pull an H plus away from water molecule, okay, and then that would free up a hydroxide ion. Okay, now the anions that are conjugate bases of strong acids and HSO4 minus are very weak and will not significantly hydrolyze. Most other ions will. Okay, so for example, HCl, okay, the conjugate base of, remember, if is what you get if you lose the H plus, right? So chloride is the conjugate base of HCl. The fact that HCl is a strong acid means chloride has no tendency to accept a proton. So it has a very low tendency to hydrolyze. Okay? Very, very low tendency to hydrolyze. It has a very low attraction for H plus. Okay? And that's why HCl is strong acid. So this is the conjugate of a strong acid. Here, HCl is a strong acid. Okay, so that sort of explains why sodium chloride is not acidic, it's not basic, because the chloride cannot pull a proton away from a water molecule to produce hydroxide. Okay, in fact, sodium chloride is neutral because sodium ion itself also does not hydrolyze. Okay, what about sodium fluoride? Sodium fluoride is basic, and so the way you would explain that, if you're asked to explain why is a salt basic, then you look at the negative ion. It must be because the negative ion can pull an H plus away from a water molecule to give you hydroxide. So you would say the hydrolysis reaction for that would be fluoride ion from sodium fluoride plus water. Okay, that gives you a weak acid, HF. H and fluoride together would give you HF, and that frees up a hydroxide. And that's the production of the hydroxide is what makes the salt solution basic. Okay? Like I said, if the acid that you're making ends up being a strong acid, then it's not very likely to happen. It's a very low tendency to occur. So chloride plus water, for example, okay, your H plus will combine with chloride to give you HCl plus hydroxide. This is not going to happen because HCl is a strong acid. This is not going to be stable in water. It's just going to fall apart right away. And then the H plus will combine with the hydroxide to regenerate water.